Hey everyone, I'm going to work a few problems for you to let you know how these determining whether or not a molecule is polar or has a dipole moment, how these problems work. So if you're given, right, the chemical formula for a compound, like any four, like you see here, Bi3, PF3, XeBr2, CH2, Cl2, it's really impossible for you to answer this question if they have a dipole moment until you determine their three-dimensional shape. So the first step is determining the Lewis structure. Let's start with Bi3. So the number of total electrons here, boron has 3 and I has 7, so, and there's 3 of them, so 21 plus 3 is 24 valence electrons. We put boron in the center as the least electronegative atom. I, and then 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. I can do a quick count because I know that everything contained here, right, when I have an atom like iodine and there are 8 electrons around it, 8 times 3 is 24. So 24 valence electrons. I've got it set. Boron has 6, but that's okay. So this electron pair geometry, okay, the electron pair geometry is trigonal planar. And that's important. The electron pair geometry and the shape are both trigonal planar because there are no lone pairs around the boron. And because each of these auxiliary groups are all I, this molecule has no dipole moment. And the reason is because we have a scenario where all of these I's are pulling along the angles of an ideal geometry, and so therefore there are no dipoles overall. Even though iodine is more polar than boron, because this is an ideal geometry, the individual polar bonds that do exist, if I were to draw the individual bond polarity, they would all point like this, with the arrows indicating the negative dipole, all pointing out, and because they're pulling diametrically at 120 degrees, this has no dipole moment. Moving on to the next problem, PF3. Phosphorus has 5. Fluorine has 7. For a total of 26 valence electrons. I'm going to put my P here. F, 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 and 2, 4, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18. So 8 times 3 is 24. There are extra electrons around this central P. So that means there are 4 repelling units. With 4 repelling units, the electron pair geometry is tetrahedral, and the shape, the molecular shape, is, with my phosphorus here, I would have one of these F's going into the plane, another F shooting out of the plane, and this third F on the right would be in the plane of our screen. So therefore, this is what's called a trigonal pyramidal or pyramidal shape. Is this polar? Well, yes, it is, because fluorine is more electronegative than phosphorus. So therefore, you could do this in one of two ways. You could show that, whoops, wrong sign. You could show that the phosphoruses have the lowercase d negative for dipole negative. This phosphorus would be D positive for a positive dipole, and the reason is because fluorine is much more electronegative. You could then draw the dipole moment for this molecule. I'm going to go ahead and draw it in red. Now there's two ways to do this. You can either show it on the side, more likely though, sometimes it's shown right through the middle. And the reason why it's shown right through the middle is because in many ways it's the summation of the smaller individual dipole or polarities, the vector sum of these individual polarities created by the bonds. So yes, this has a dipole moment. The fluorines are the partial negative end. The phosphorus is the partial positive end, and that's denoted by the cross here. So the end that looks like a positive is the positive, and the arrowhead, the tip of the arrow, is the negative end of the molecule. Okay? XeBr2. Let's take a look. XeBr2, we have 8 valence electrons for all the noble gases except for helium. And 7 for bromine times 2 is 14, so that's 22 valence electrons. If we put our X in the center, this X has got to have, right, some lone pairs around it. 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. So now we have 8 times 2 is 16 valence electrons. 17, 18, 19, 20, 21, 22. Ooh, this is going to be a fascinating structure. Now, with 5 repelling units, 1, 2, 3, and then 4, 5 with the bonds, the electron pair geometry for XeBr2, right? The electron pair geometry is going to be trigonal bipyramidal. The molecular shape is going to be linear. And the reason it's going to be linear is because you have your xenon in the middle, and when we have a choice where the lone pairs are going to be, right, they go around in a plane, right? The flat plane that creates 120-degree angles here in the equatorial position around the xenon, and then you have a bromine above and a bromine below. And because even though bromine is going to be much more electronegative, right, and these individual bonds are polar, the overall dipole moment is 0 because this is actually a linear molecule. And we put the lone pairs in the center around the equator, right, in the equatorial position, because if a lone pair was above or below, that means that there would be a 90-degree angle, and lone pairs are more repulsive than bonded pairs. So to minimize this, that means that there are some 90-degree angles, but those 90-degree angles are between non-bonded and bonded. None of the 90-degree angles are between non-bondeds. So by putting all the non-bondeds in the center at 120 degrees apart, we minimize repulsions. So this is going to be a linear molecule, and because both Br and Br are the same element above and below, it's going to be nonpolar. So for the sake of argument, what if this was a fluorine instead? Then you would have a polar molecule. Because fluorine is more electronegative than bromine, and it's still linear, it would create a molecule in which the fluorine side becomes partially negative and the bromine is partially positive. Let's do our last example, CH2Cl2. That's called dichloromethane, CH2Cl2. So let's see, with 4 valence electrons plus 2 plus 14, we have 20 valence electrons. Okay, we put our least electronegative, the one that needs the most bonds, in the middle. H, H, Cl, CO, 1, 2, 3, 4, 5, 6, 1, 2, 3, 4, 5, 6, 1, 2, 3, 4, 5, 6. And let's see. How many valence electrons do we have? 8 plus 8 is 16. And then, ooh, I made a boo-boo. I went a little bit crazy there. It looks like I put some valence electrons around that hydrogen that I shouldn't have. Okay, let's get back to doing this problem. So, we have 8, and 8 is 16, 17, 18, 19, 20 valence electrons. The question is this polar? Well, it would obviously take a tetrahedral geometry, and what you start to notice when you think in 3D is that there really is no difference how I chose to lay these out, right? So whether or not I decided to write them in this way or put one of the CLs on top, switching it off for a hydrogen, it actually doesn't make a difference. And every single time you would come up with the same scenario that while pure methane would be nonpolar because they're all hydrogens, this side of the molecule, when 2 of these are chlorine, creates a negative dipole side, and then this becomes the positive dipole side. So, truth, this is a polar molecule. And if I were to draw, I would do something like this, where the positive end is toward the hydrogens and the tip of the arrow is pointed toward the chlorines. So those are 4 examples for you where I've worked out how you can tell whether or not something is polar or nonpolar, whether it has a dipole moment or doesn't. Good luck with the rest of your practice problems.